Hello, my name is Jeremy Satterfield. Thank you for taking the time to view my presentation today, and hopefully you're all staying safe and healthy out there. So today I'm going to be talking to you about improved manufacturing methods for hail simulates and impact testing. Now, hail can be a problem for us on the ground, causing property damage to homes and cars, but it can be a much bigger problem if you're traveling in high velocity at 30,000 feet in a metal pressurized tube. So as you can see, it can be a much bigger problem for aircraft, and it's something that needs to be taken into account in the design phase. Now, one of the reasons hail can be a big problem for aircraft is it's invisible to radar, one, and two, it's unpredictable. It's hard to tell which storms will produce hail and which storms won't, and also where in the storm the hail might be produced. So it's not exactly something the pilots can detour around or try to avoid. So unfortunately, it's something that the inevitability of hail impacts needs to be taken into account during the design phase of the aircraft and the fuselages. But unfortunately, there's really not a lot of consistent data out there to aid the aircraft designers in making future designs of fuselages. So it's something that we have to do further research on. Now, there has been a lot of research in the past of hail impact, but unfortunately, because of the complexity of the interaction between the hail ice and the test object, computer-based dynamic analysis doesn't really give us very good results. So we're left with experimental impact testing, which is usually firing a hail simulate at high velocity at a test object, such as an aircraft panel or fuselage. And that's done in this case with a 12-foot compressed air gas gun, as you see in this picture. This kind of testing can also be useful for composite fracture analysis and delamination analysis, as well as failure mode designation. Now, the previous methods of this type of experimentation yielded inconsistent data. And that's because most of them focused on either the firing mechanism or the sensor array to record the data, but didn't really put a lot of thought into the actual hail simulate itself, which is rather unfortunate because, in my opinion, that hail simulate is really the center of this experiment, creating a hail simulate that really replicates what a naturally formed hailstone is that forms out in nature. Now, most of the previous methods used a pour-in mold, which is where you pour the ice into a spherical mold and you freeze it. But unfortunately, because of the way ice freezes, it yields impurities and cracks in the ice, and the ice tends to fail in a way that a natural hailstone wouldn't. So it really doesn't give you great data, and it also doesn't give you very accurate data. So it's really clear that we need to make a better hail simulate that better simulates naturally formed hail. And the first place we should start is how hail actually forms in the first place. So if you look at how hail forms, basically supercooled water droplets are carried to high altitudes above the freezing line by updrafts in a supercell storm. That supercooled droplet will freeze and will fall back down below the freezing line, where moisture will accumulate on its surface in a thin layer. Then updrafts will carry it back up above the freezing line, that moisture will freeze, and that convection process will continue, and layer by layer, that hailstone will begin to grow. Now, it will eventually grow to where it's so heavy that the updraft can't carry it anymore, and it will fall to the ground as we experience hail down on the ground. If you've ever seen a hailstone, you might see it looks kind of cloudy, it might be oblong or non-spherical. That's because as hailstones grow to the size to where they fall to the ground, you don't get as clean as pure ice. You get air bubbles and you get different shapes. But aircraft are encountering hail up at their cruising altitude, where they're encountering hail in the middle of its forming process, where they're essentially encountering the core of a hailstone, which is a very dense and very impurity-free, clear sphere of ice. And that is really what we need to replicate if we're going to get good data to better design our aircraft fuselages. So creating better hail can be divided into two basic problems. The first is making clear ice with less imperfections, and the second is making that ice spherical. Unfortunately, not with a chainsaw like you see in this video. So How do we make clear ice? Well, we have to first start with impurity-free water, and that means either boiled water or distilled water, but we also have to take into account those air bubbles that naturally form in water, and you have to use a vibrating table to remove those air bubbles. And then now that we have impurity-free water, then we have to make it into clear ice. After doing a lot of testing and research, we found that the best way to do this is to control the temperature gradient in that freezing ice block. So as water freezes, the impurities tend to stay in the liquid portion of that freezing water. So if you can control the direction of the freezing, you can force any of those impurities into the last remaining liquid. The best way to do this is to use a rectangular container with 5 of the 6 sides insulated. This allows you to expose only one of the sides to the cold and essentially allows you to control the direction of that freezing. And as you can see on the picture on the right, all of the impurities are forced to one side of the ice block, and you can simply cut that off and you're left with clean, impurity-free ice. Now we have to take that clean, impurity-free ice and make it into a sphere. Looking back at some of the research NASA had done, they had used an ice press that uses high pressure to take that ice block and turn it into a sphere. Unfortunately, that caused some stress fractures, and because stress fractures are unpredictable, that didn't give very consistent results. So we decided to take that design and kind of improve upon it, still using some pressure, but also using the thermal conductivity of aluminum to actually melt the ice into the sphere shape. This is essentially subtractive manufacturing, where we're taking away what we don't want and leaving what we do want. But the advantage of this is we're leaving the ice sphere free from the impurities and free from any additional stress fractures or impurities we're adding in the manufacturing process. And we're not undoing all that hard work we did to get the clear ice in the first place. To create this ice press mold, first we designed it on the computer with a CAD program, and then we used computer-aided manufacturing in a CNC mill to actually create the ice mold to a very precise degree to get those perfect spheres. Now, computer-aided manufacturing has a bit of a learning curve because you're essentially telling the computer what you want and it's interpolating that into code to tell the CNC mill what to do. So we went through a few iterations, but eventually we finally got to a very nice end product. This end product worked as intended, met all the requirements that we set out for, and created replicatable and consistent hail ice simulates that we were able to use in testing. Now, in the future, and we wish to advance this to actually use these hail ice simulates and this mold design with the Impact Group Lab to making more accurate and consistent hail for better impact data. And we're also going to use a sabot design from a previous student research project in conjunction with this to use in the gas cannon. And of course, we can't finish this off without showing you what the final product looks like, a very nice spherical, impurity-free hail ice simulant that really closely replicates what the aircraft would encounter during their cruise, and allowing designers to take that data and really further the design of aircraft fuselages to make flying safer for us, not having to worry about those hail impacts really having a catastrophic effect on aircraft as they do today. So I want to thank you for your time, and I look forward to the Zoom Q&A session in the future. Thank you.